I'm back. Kind courtesy of in Ghana. So last week I asked you to watch the remaining section of the lecture online. Okay, and then we'll have a brief discussion.
No, I'm done cooking. What did I like with some stew?
Hey, that is very nice. I like that.
Yes.
Oh, hello. Yeah, so I asked you that you should watch the video on YouTube, and then we can have a brief discussion on that lecture before we continue today. Any questions from the previous lecture and from the videos you watched? Any questions? Kobe, did you watch the video? Kobe, did you watch the video? Richard?
I didn't finish everything. Data.
Okay. Any questions from what you watched?
No, not really.
Okay.
But I'll go back to it.
Okay, Gabriel.
Yes, sir.
Did you watch the video?
Yes, I watched it.
Any questions?
So on the video, no, but I would like to make a suggestion. If you can briefly go over the assignment questions.
Assignment. Assignment
Yes,
one.
assignment. Yes, sir.
Assignment one. Okay. Okay, fine. So I think we'll look at that at the tail end of the course. Then who else? Kobe, you've not given me an answer whether you watched the video. Okay, so then let me assume, because you don't have any questions, then it means
Hello,
that
sir.
the video was clear enough, right? So I want to assume that once you don't have questions, the video is clear enough. So we want to continue with the continuous runoff variable. Then I'll also incorporate Gabriel's suggestion to the tail end of the today's class. And I'm sure the technical guys have contacted you with regards to the quiz. Have you heard anything from the university? Have you heard anything?
Nothing. Nothing.
No, sir.
Okay. 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 That's fine, but it will be rectified. I'm sure that those errors will not be experienced in the next quiz. Okay, they'll rectify that for you. And I also see to the quiz one, okay, with regards to your scores and all that. Your job is to submit your solution. Mine is to mark and make decisions. Theirs is to fix the system. So if there's a challenge somewhere, I know what to do at the end of the day. Okay, so let's not bother too much about that. Okay, so we want to begin today's class. As you are aware, I sent you the lecture note for lecture 3 and 4. Okay, so you should have the lecture notes on your WhatsApp page. We want to watch the video. Yeah, and I'm on standby. If you have any question at any point in the video, just raise your hand. I'll pause it, address your question before I continue with the video. Okay. Yeah, so we'll look at a little bit of the last part of last week's class because we'll need to continue from there. So we'll play a little bit on the property of the discrete random variable.
And the variance is also going to be the expectation of L squared minus expectation of what? X. Okay. Technically, this is just the expectation of what? The expectation of X, the process, minus what? Mu squared. Okay, we know this. We know this from the previous class. Okay. Oh, yeah. The variance is just what? The expectation of the square deviates. Okay. Of the square deviates. So that gives us the expectation of S square minus the expectation of what? X square. Okay. So in finding the variance of the process, okay, look at it carefully. Right, expectation of X square is going to be like this. It's just like finding the expectation of X, but this time you have to square the X and multiply by their probabilities. Okay, but for this component, it is the same expectation of X. Okay, this should look like this: expectation of X all square. Okay, good. So the expectation of X is what we have up here, which is summation of xi times p of xi. So in other words, when you're finding the variance, all you need to find is this quantity, the first term here, okay? Because you would have found this, which is already the expectation of X. You would have found it for the mean. So you don't need to find the second quantity here. You only find this quantity, okay? And then come and subtract the square of the mean you found earlier from it to get the variance. Okay, so take note of the formula. Take note of the formula if.
Okay, so let me pause here. The main formula we are going to need in the next phase for continuous random variable is what we have here, okay? So the variance as well as the expectation of the process, okay? So this is for a discrete random variable, and because of that, we call it the probability mass function, okay? But for continuous random variable, we are going to look at PDF, that's the probability density function. And it's just an extension of these formulas we have over here, okay? So you take note of that. Now, let me see, let me just fast forward a bit, and then I'm sure you've watched this video already, so we don't need to waste my time here. So I'm going to play the video for today's class, that is the properties of a continuous random variable. Okay, so we want to begin today's class. Okay, last week we started with probability concepts. That's the fundamental of probability, where we looked at some what probability is about. Okay, and we looked at rules on probability, the additive rule, multiplication rule, conditional probability, the Bayes law. Then, yeah, I forgot to ask Gabriel, how is the sound before we continue? Probability distribution, okay, where we looked at what a random variable is, what the probability distribution is, okay, as well as looking at how to generate a random variable, the probability distribution for a random variable. Then we also looked at the specifically a discrete random variable and the properties
of the discrete random variable, okay? And then we solve some few examples, okay, with regards to finding some values of k, and then writing out the probability mass function given a particular probability function, okay? And we wrapped up on the properties of the PMF, okay? For example, the mean, okay, of a discrete random variable. Today we want to continue from where we left off. Okay, we ended off by finding the mean of a discrete random variable. Last week we said that the variance is also giving us the expectation of s squared minus the expectation of x all squared. And we said that the expectation of x is mu squared, okay? Mu, the expected value, which is the mean value, right? So in the estimation of the variance, okay, what you need to find is the expectation of x squared, which in itself is given as the summation of xi squared times p of xi. Yeah. So in that case, all you need to do is to find the expectation of x squared, okay, and you subtract the square of the mean value, okay, to give you the variance. So as an example, we've been given the probability function as kx, okay, for x1, 2, 3k into bracket 4 minus x for x3 and 4. Okay, we have to find the variance. So we want to find the variance, okay? Good. So let's see how to solve that. So in estimating the variance, you can create a table like we have here, okay? So you create a table with the formula for the variance, okay? var x is what? Is summation x, okay, squared times p of x, okay, minus the expectation of x squared, okay, which we calculated last week. So all we need to add is to so all we need to do is to find what or create another row for x squared. This is it, that's the square of x. So 1 square will be 1, 2 square will be 4, 3 square will be 9, 4 square is 16. Then next you multiply x square with p of x, okay, because you are required to find the product of s square times p of x. So that will give us 1 times 1 over 6 will be 1 over 6. Then 4 times 2 over 6 will be 8 over 6. 9 times 3 over 6 will be 27 over 6. And then 16 times 0 will be what? Will be 0. Okay, so that gives us s squared times p of x. Okay, then next we have to sum it up, right? So in summing, this is it. This is the summation here, summation. That gives us 36 over 6, which equals to 6. Okay, and then we've already found the mean, mu to be what? 2.33 from last week. Okay, so your variance is equals to 6 minus the mean what? Square, okay? The square value of the mean. So 6 minus 2.33 square, when you do that estimation, you get 0.571. So that gives us the variance for a discrete random variable. Okay. Now to proceed, good. So that wraps it on the discrete random variable, okay, which we should have ended last week, okay, but due to poor network, we had to omit that session. This week we are looking at probability continuous random variable, or what you refer to as CRVs, okay. Now, when we talk about continuous random variable, we are talking about random experiments which occur continuously, okay? So continuous process. So for example, the time to the first phone call is a continuous process, okay? We are not sure if the phone call will even happen, but how do we estimate the probability to the time of the first phone call, okay? Those processes are what? Continuous random variables. Okay, so there are some few things we need to know about continuous random variable. The first thing we need to know is that the probability distribution of a continuous random variable has a special name, which is what? The probability density function. Okay, the probability density function. Good. So the name for the probability distribution of a continuous random variable is the probability density function, which is PDF. Okay, good. And like the PMF, we can also write this as a function, okay, f of x. Okay, good. Now, there are other things we need to know. We say that the probability of a process A, okay, given at a point, okay, is always equals to what? It's always equals to 0. So the probability of the process, the random variable being equal to a particular point, is going to be equal to 0. In other words, the probability of remaining at a point is what? Always equal to what? 0. Okay, good. Then we say that for a continuous random variable, we calculate the PDF, okay? We say that the probability of the process is always greater than or equal to what? 0 over the domain of x. And also the integral of f of x over the domain of x with respect to dx is equal to 1. We know integration is continuous summation, okay? In the case of the discrete random variable, we had what? The summation of what? F of x, okay, over the domain of x, that's from I equals to 1 to n, is equals to what? Is equals to 1. Good. Then if the probability of the process is equal to 0, then it means that what? If it's equal to 0, if fx is not what? In the domain of what? Of x, okay? Or in Rx. Very good. Now, for the cumulative distribution, okay, similar to the discrete random variable, let me clear everything. Similar to the discrete random variable where you have summation, okay, from xi to a given point x. Okay, here we are going to integrate You see the similarities. So summation becomes what? Integration. Okay, from the lower bound, which is negative infinity, okay, to the point what? To the point x. Very good. So in the case of a continuous random variable, the CDF is estimated using what? Integral from lower bound towards the point x. And the expected value of the process, which is the mean, is the integral from negative infinity to positive infinity. That is from the lower bound to the upper bound, okay, of x times f of x dx, okay. So in the case of the discrete random variable, it was summation over the bound of x, f x times what? P of x, okay. So it's the same thing. This time it is integration from the lower value to the upper bound of x, okay, and then we are integrating with respect to what? To the dx, okay. Very good. It's very similar. Good. And if we need the variance, okay, then similar to that for a discrete random variable, we can also write, okay, that the variance is equal to what? The expectation of what? X squared. The expectation of x squared, okay, minus the mu of x, okay, mu of x squared. Good. So mu of x, like we said, for the discrete case, would have been calculated using this formula. So you don't need to calculate it again, right? This is a formula, okay? So you would not need to recalculate the expected value, okay, when finding the variance, especially when you've already found the mean. So all you need to find will be the expectation of x squared. And the expectation of x squared will also be what? S squared times f of x, meaning you are replacing what? X in this formula here with what? With x squared. Okay, and the integration is from the lower boundary to the upper bound, okay? That's the lower limit to the upper limit. Very good. So you take note of this formula.
Yeah, I hope you've taken notes.
Okay.
Formulas. Class, I hope you've taken note of the formula. Hello?
Yes, sir.
Okay. I'm continuing with the video.
I'm proceeding.
Okay, sir.
Take a note on which summarizes these equations. Okay, then we come and take some examples on what we've looked at so far. So for the discrete random process, okay, we have discrete values like x, 0, 1, 2, 3, 4. Okay, but in a continuous random variable, we have an infinite sample space, okay, which is over an interval. So from 0 to 1, you have infinite number of what? Values within the interval, okay? Good. And then when you come here for a discrete mass function, that's PMF, the probability is usually written as P of xi, okay, whilst when it comes to probability density function, we prefer using f of x, okay? Good. And then for the same properties where we have P of xi is always greater than 0, here we write f of x is also greater than 0 for x within the domain R of x, okay? Good. Then we have a summation of what? All probabilities equals to 1 from 1 to what? Infinity, okay? In the case of a continuous random variable, will be the integral of f of x dx is equals to 1, okay? Good. Over the domain of x. Then finally we have what? If f of x is equals to 0, meaning the probability is equals to 0, then x is not what? in the domain of X in the first place. Okay, and the CDF2, similar to what we have here, it becomes integral, okay, from X, from the lower bound to the point X, okay, with respect to what? With respect to T, okay. Good. Now, if it's within two limits A and B, then the cumulative density function becomes what? The integral of f of x from what? A to what? To B. I'm sure you've taken note of these formulas as well. Okay. Now we have a first question here. Okay, we are told that a live ball of Variance, okay, has a density f of x is equal to k raised to the power k e raised to the power 0.1x. Okay, that's an exponential function. Good. Over the r of x, which is what? 0 to 10. Okay, and so the domain of x is infinite from 0 to what? To 10. Okay, and 0 otherwise. We have to find the value of k. Okay, good. Which reminds us of the sample we looked at in the PMF. Okay, anytime we have to find the value of k, what we do first is to rewrite the table and then sum the values and equate to 1. Then we look for the value of k, right? So which means that the principle here, or the idea here, is then the summation of all what? F of x over the domain should be equal to what? Should be equal to 1. Okay, if we integrate the function over the domain of x from the lower limit to the upper limit, it should give us 1. Okay, then based on that we can find the value of k. Okay, so let's proceed and work that out. Okay, so in calculating this, we are going to get make f of x, okay. Let me rewrite this. Good. So what we are saying, what we just said, we are saying that, just a minute, let me clear the screen. Okay. Since we are not in slideshow mode. Okay. So what we are saying is, if we're to integrate, okay, over Rx, the function, okay, with respect to x, that should give us what? 1. Okay, and the domain was clearly stated from 0 to 10, okay, which implies that we are going to integrate the given function, which was what? K e raised to the power negative 0.1 x from the limits. Let me change the color here. So from the lower limit, which is 0 to what? To 10. Okay, and then we integrate with respect to what? Dx, which will be equal to what? 1. Okay, good. Now, because k is a constant, okay, then we can pull it out of the integration sign, okay. So then we have k, okay, integral of e of x, e raised to the power negative 0.1 x from 0 to what? To 10. Okay, good. And then once we have that, we'll have to integrate. We have to integrate e raised to the power negative 0.1. Okay, negative 0.1 with respect to x. Okay, and then integrating e raised to the power negative 0.1. Okay. Negative 0.1, we're going to get what? K, okay, and then when we integrate the function, we get e raised to the power what? Negative 0.1 x, okay, over negative 0.